All right. So, welcome to the beginning of the chemical bonding and compounds unit. All right. So far, when we've been talking about atoms, we've only talked about them as being independent of each other. All right. And the thing about most atoms that you'll find in nature is they're not individual atoms, but they actually are going to combine with other atoms to make compounds. All right. Um, so So there are some atoms out there that are perfectly happy to stay as individual atoms, but most atoms are going to want to combine. So the question is, why would an atom choose to combine with another atom versus if it, wanting to remain individual? And the answer to this is to gain stability. Stability. Spell that right. Okay, so an analogy, why does a domino fall over? All right, the reason that it falls over is that the fallen over domino is more stable, and another way to say that is that it has less energy than the upright domino. Okay, so even though these notes say recall the octet rule, this is going to be the first time introducing this. There's this thing called the octet rule, which states that atoms tend to prefer to gain or lose electrons to gain the stable electron configurations as the closest noble gas. All right, I know that's a mouthful, but it will make more sense when you see an example of it. All right, an oversimplified way of saying that is that atoms tend to like to either gain or lose electrons so that they will have 8 valence electrons. All right. So any atom, if it's stable, is going to want to have those 8 electrons. All right. There's one exception to that, which we will talk about. All right. So this explained why. This explains why metal atoms tend to prefer to lose electrons to make cations, and cations are positive ions, while nonmetal atoms tend to gain electrons to make anions, all right, which are negatively charged ions. So this here's just a picture of the periodic table. And what I was saying is that these parts of the periodic table, these are the nonmetals, all right? And those parts are the ones that are going to want to, gain electrons. Sorry about the effect there. So these ones are going to want to gain electrons in order to become negatively charged ions. And the metals, especially the metals that are over in this region over here, but this is going to eventually include all of these metals. It's just it's a little bit more complicated when you talk about the ones in the middle. These are going to want to make those are going to want to lose electrons to make positively charged ions. All right, so let's take a look at why this happens. All right, so to explain this, I'm going to use the original definition that I gave, which is that they tend to gain or lose electrons to achieve the configuration of the closest noble gas. So let's use neutral fluorine as an example. All right, the question would be, would fluorine tend to want to be the type of atom that wants to gain or lose electrons? All right, well, this is its configuration right here. All right, so what you're going to want to do is you're going to want to locate the closest noble gas. All right, and remember that the closest noble gas might be on the same period with it, or the same row, or it might be on a different row. All right, so if you find fluorine, it's right here on the periodic table, and the closest noble gas is right next door, which is neon. All right, so let's write that down. And this is neon's configuration. So you have to ask yourself, what does fluorine have to do in order to get this configuration? All right, and hopefully you can see this has one fewer electron than this. So this would have to gain one electron in order to have this configuration right here. So it's going to gain an electron so that it now has this configuration right here. The thing about this is that this, in order for fluorine to be neutral, this is the number of electrons that it needs. All right. When it gains that one electron, it now has one extra electron. All right. It has one extra electron compared to protons. And so therefore, when it gains that electron, it is no longer neutral. It would actually be F minus. All right. So another example we could do with this would be for sodium. All right. Okay. And so if I drew the electron configuration for a neutral sodium atom, this would be it right here. All right. So recall, it wants to have the same number of electrons as the closest noble gas. All right. So if you take a look at the periodic table right here and you find sodium, right? Sodium is right here. All right. And so you might be tempted to just go over, just kind of slide over to the right on that same row and find the noble gas. But remember, sometimes the closest, in terms of numbers, is not on the same line. All right, sodium has got an atomic number of 11, but neon on the line above it has got an atomic number of 10. So the closest noble gas to sodium is actually neon. All right, so, and we've already drawn the configuration for neon, which is right here. And so here you're going to ask yourself, what do we have to do to this configuration right here so that it would have this configuration right here? And in this case, this guy's going to have to lose one. All right, it's going to want to get rid of this 3s1 electron. Okay, and so just like before, in order for these atoms to be neutral, they have to have a certain number of electrons. For sodium to be neutral, it needs to have this number of electrons right here. So when it loses that one electron, it's no longer neutral. All right, it now, if it has only this number of electrons, it now has one fewer electrons than it does protons, and therefore it's going to be positively charged. All right, so you'd put a little plus right there. So there's also a more generic form of the octet rule, which is to state that atoms tend to react in ways so that the atoms will have the same number of valence electrons as the closest noble gas. All right, it's a little bit less wordy than the one where you're talking about the configurations, but still it's going to apply. All right, so as an example of this, let's consider a neutral lithium atom that would happen to collide with a neutral fluorine atom. And so just to point out, when we were talking about the models of the atom, we mentioned that there were two models. There's the Bohr model, which was not technically correct, but it was simple. But then there's the quantum mechanical model. All right, and so this is an example of one of these times where you use the Bohr models to explain things, even though we know that this representation is not accurate. Like we know that literally we don't have the electrons at this constant distance away from the nucleus. It still provides a relatively simple way to explain this concept. All right, so this is a good application of using this. All right, it's kind of like using stick figures to explain something. They don't really look like real human beings, but it gets a point across very simply. All right, so if you take a look at lithium right here, we could represent this as Li0, and the 0 means neutral. All right, this guy right here would be fluorine, neutral. All right, and so if you take a look at this and say, what does this atom want to do in order to become like the closest noble gas? Well, the closest noble gas to lithium, if you looked at it on the periodic table, would be helium. All right, and so therefore, and helium is going to be just has 2 electrons, so it's just going to be that central part right there. So what it wants to do is it wants to lose 1 electron. All right, this fluorine right here, its closest noble gas is neon. All right, which is 1 to the right of it. So in order to have the same number of electrons as neon, it wants to gain 1 electron. All right, so let's so think about this. If you had 2 atoms right next to each other, and one of them wants to lose an electron at the exact same time that one of them wants to gain an electron, hopefully you can see what's going to happen. All right, there's going to want to be a transfer of an electron. Okay, so I've gone ahead and changed the color of that just for emphasis. So if this guy wants to lose an electron and this one wants to gain one, well, what happens if this guy gives this electron to this atom right here? You would then have these. All right, this one's now missing that outer electron. This one now has an extra electron. All right, and so when this happens, remember when you gain or lose electrons, it's going to affect your charge. All right, so when this happens, your lithium is no longer neutral. Remember, for it to be neutral, it needed to have 3 electrons. It's only got 2 now, so it now has a positive charge. All right, your fluorine now has an extra electron, making it a negative charge. All right, so the thing about these two atoms is they now have a reason to want to stick to each other. And that's because this is now positively charged and this is negatively charged, and positive objects attract negative objects. All right, so these two guys right here, they are going to want to stick to each other. So these guys are going to want to stick to each other, all right? And they stick to each other because they have opposite charges, all right? And whenever you have things that want to stick to each other because of opposite charges, you call that kind of stickiness an ionic bond, all right? And we're going to contrast that to a different type of bond in just a second. But first, I want to show an example of this right here going on, all right? Because this is obviously done, I would say on paper, it's not on a computer. But like, remember, these represent real atoms, and there are real atoms that could actually do that. And I'm going to show that in the very next video. So watch the next video. This actually shows neutral sodium atoms doing this exact same thing with neutral chlorine atoms. And if you look at the electronic structure, you would realize that sodium would be kind of like this atom wanting to lose an electron, and chlorine would be kind of like fluorine where it wants to gain an electron. All right.